Today we are going to discuss on chapter 10. The title of chapter 10 is Classification of Operators over Hilbert Spaces. The representation theorem for functionals over Hilbert spaces will enable us to define Hilbert adjoint operators for a bounded linear operators over Hilbert spaces. This problem was suggested by the solutions in matrix equations, solutions of linear differential equation and integral equations. Later we will see that Hilbert adjoint operator helps us to define a class of operators, namely self adjoint operators, normal operators and unitary operators. Also we shall discuss on special type of operators called projections operators. Projection operators are very simple and it has a lots of applications in various branches of mathematics. Also self adjoint operator, normal operators and unitary operators has a key role in applications of mathematical problems. With this we are now going to start on module 1. In module 1 we shall discuss on some preliminaries of Hilbert adjoint operator and some algebras of Hilbert adjoint operators. Let H be a complex Hilbert space and let BD LHH be the collection of all bounded linear operators from H onto itself. Let T be a bounded linear operator from H onto H, that is T belongs to BD LHH, and let Y belongs to capital H be fixed. Define Fy from H to C by Fyx equal to inner product Tx comma y for all x belongs to H. It can be easily shown that Fy is linear and also Fy is a functional, that means Fy is a linear functional. Now modulus Fyx equal to modulus inner product Tx comma y, which is less or equals to norm Tx into norm y, which is less or equals to norm T and norm x into norm y. So Fy is bounded, that is Fy belongs to H star. So by Ridge representation theorem, for Fy belongs to H star means the collection of all bounded linear functionals over H. There exists a unique Y star belongs to capital H such that Fyx equal to inner product x comma y star for all x belongs to capital H. Thus for Fy belongs to H star we get Y star belongs to capital H. Let us now define a map T star from H to H by T star y equal to Y star. So Fyx equal to inner product x comma y star, which is equal to inner product x comma T star y for all x belongs to capital H. So inner product Tx comma y equal to inner product x comma T star y for all x belongs to capital H. Thus for T belongs to BD LHH we get a map T star from H to H. So T star is called the adjoint of T. Now T star is well defined. If possible, let T1 star from H to H be such that inner product Tx comma y equal to inner product x comma T1 star y for all x belongs to H and for all y belongs to H. Also we have inner product Tx comma y equal to inner product x comma T1 star y for all x belongs to capital H and for all y belongs to capital H. So inner product x comma T star y equal to inner product x comma T1 star y for all x belongs to capital H and for all y belongs to capital H, which implies that inner product x comma T star y minus T1 star y equal to 0 for all x comma y belongs to H, which implies that inner product x comma T star minus T1 star y equal to 0 for all x comma y belongs to capital H, which implies that T star minus T1 star y equal to 0 vector belongs to capital Y for all y belongs to capital H. This means T star minus T1 star equal to the 0 operator on H. So, T star equal to T1 star. Also we have inner product Tx comma y equal to x comma T star y for all x comma y belongs to capital H. Let y1 comma y2 belongs to capital H. Now, inner product x comma T star y1 plus y2 equal to inner product Tx comma y1 plus y2, which is equal to inner product Tx comma y1 plus inner product Tx comma y2, which is equal to inner product x comma T star y1 plus inner product x comma T star y2, which is again equals to inner product x comma T star y1 plus T star y2 for all x belongs to capital H. So, T star y1 plus y2 equal to T star y1 plus T star y2. This shows that T star is additive. Similarly, we can show that for all alpha belongs to C, C means the collection of all complex numbers, we have T star alpha y1 equal to alpha bar T star y1 for all y1 belongs to H. Now, inner product x comma T star alpha y1 equal to inner product Tx comma alpha y1, which is equal to alpha bar Tx comma y1, which is equal to alpha bar inner product x comma T star y1, which is equal to inner product x comma alpha double bar T star y1, which is equal to inner product x comma alpha T star y1. So, T star alpha y1 equal to alpha bar T star y1. So, T star from H to H is linear. For an element y belongs to capital H, norm T star y square equal to inner product T star y comma T star y, which is equal to inner product T star y comma y. So, norm T star y square less or equals to norm T star y into norm y, which is less or equals to norm T into norm T star y into norm y. Thus, norm T star y less or equals to norm T into norm y, implying that T star from H to H is a bounded linear operator. Also, supremum over y not equal to 0 vector of norm T star y divided by norm y less or equals to norm T. This implies that norm T star less or equals to norm T. This is equation number 1. We shall now show that T double star equal to T for y belongs to capital H, inner product Tx comma y equal to inner product x comma T star y for all x belongs to capital H. This is equation number 2. Replacing T by T star, we get inner product T star x comma y equal to x comma star of T star y, which is equal to inner product x comma T double star y for all x comma y belongs to capital H. This is equation number 3. Interchanging x and y in H, in equation number 3 we get inner product T star y comma x equal to y comma T double star x. Taking conjugates of both sides, we get inner product x comma T star y equal to T double star x comma y for all x comma y belongs to capital H. This is equation number 4. From equation number 2 and equation number 4, we get inner product Tx comma y equal to inner product T double star x comma y for all x comma y belongs to capital H, which implies that Tx equal to T double star x for all x belongs to capital H, which implies that T equal to T double star. This is equation number 5. From equation number 1, we get norm T star is less or equals to norm T. Replacing T by T star, we get norm T double star less or equals to norm T star, which implies that norm T less or equals to norm T star, because already we have proved T double star equal to T. From equation number 1 and this equation 6, we get norm T equal to norm T star. The operator T star from H to H is called the adjoint of the operator T. Sometimes we call it Hilbert adjoint operator. Thus, we get the following theorem. Thus, the statement of the theorem looks like this. Let capital H be a complex Hilbert space and let T belongs to BD LHH. Then there exists a T star belongs to BD LHH such that norm T equal to norm T star. It is to be noted that the adjoint of the identity operator I from H to H is the identity operator itself. Similarly, the adjoint of the null operator from H to H is the null operator itself. Clearly, I star and star of the null operator belongs to BDLHH with norm of I equal to norm of I star and norm theta equal to norm theta star, where capital theta is the null operator. Thus, we pose a problem. Define an operator T from L2 to L2 by Tx equal to sequence 0, x1, x2, dot dot dot, where the first coordinate is 0 for x equal to sequence x1, x2, dot dot dot, xn, dot 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 belongs to L2, where the usual inner product on L2 is defined. We shall now find the form of the adjoint of capital T. Let T star be the adjoint of capital T. We have inner product T star x, y equal to inner product x, ty for x, y belongs to L2. Since ty equal to sequence 0, y1, y2, dot dot dot, yn, dot 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 for y equal to sequence y1, y2, dot dot dot, yn, dot 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 belongs to L2. We have inner product T star x, y equal to inner product x, ty, which is equal to sigma n equal to 1 to infinity xn plus 1 yn bar, which is equal to inner product sx, y say, where sx equal to sequence x2, x3, dot dot dot. Hence, we have inner product T star x, y equal to inner product sx, y for every x, y belongs to L2. Since T star is unique, we have T star equal to s, so that T star x equal to sequence x2, x3, dot 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 dot. Now, let us cite an example. Let capital M be a subspace of small L2 consisting of all real sequences, each one containing only finitely many non-zero terms. Then M is an incomplete inner product space with the same inner product for L2 given by inner product x, y equal to sigma n equal to 1 to infinity yn into xn, where x equal to sequence x1, x2, dot dot dot, xn, dot 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 belongs to L2, and y equal to sequence y1, y2, dot dot dot, yn, dot 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 belongs to L2. This is equation number 7. For each x belongs to capital M, define Tx equal to sequence the first coordinate sigma xn by n, 0, 0 and so on. This is equation number 8. Then for x, y belongs to capital M, we have by definition inner product Tx, y equal to y1 into sigma n equal to 1 to infinity xn by n. This is equation number 9. Let us take En equal to 0, 0, dot dot dot, 1, 0, 0, dot dot dot, where 1 is taken in the nth place. Then using equation number 9, we get inner product Ten, E1 equal to 1 into sigma j equal to 1 to infinity Enj divided by j, which is equal to 1 by n. We shall now verify that whether an adjoint operator T star, which is the adjoint of capital T, exists. Now, inner product En, T star E1 is equal to T star E1 into En, where the right hand side gives the component wise inner product. Since T star E1 belongs to capital M, T star E1 into En cannot be equal to 1 by n for all n equal to 1, 2, 3, comma and so on. This shows that there is no T star on M such that the adjoint operator T star of T exists. In this connection, we note the following remark: the completeness property of an inner product space cannot be relaxed. Up to this, we have learned for a given bounded linear operator over a Hilbert space H onto itself, there always exists a unique bounded linear operator T star from H to H, where T star is called the adjoint of the operator T. Also, we have shown that T star is well defined, and we have shown its linearity and its boundedness property. Also, we have proved some properties, that is T double star equal to T. Also, we have cited an example of an existence of an adjoint operator of a bounded linear operator T. Also, we have shown non-existence of adjoint operator of a bounded linear operator T. Now, we shall discuss on some algebraic properties of adjoint operators. That is, if T1 and T2 is a bounded linear operator over a Hilbert space H onto itself, then T1 plus T2 is again a bounded linear operator. If T is a bounded linear operator from H to H and alpha be any scalar, then alpha T is again a bounded linear operator. Now, we shall show that T1 plus T2 star equal to T1 star plus T2 star, and alpha T1 star equal to alpha bar T1 star, where alpha is a complex number. Also, we shall show that T1 T2 star equal to T2 star T1 star. Also, we shall see that adjoint of the inverse of the operator exists, and what is the form of the adjoint of the inverse operator. Now, we are going to discuss on algebra of adjoint operators. Let capital H be a complex Hilbert space, and let T1 and T2 be two bounded linear operators mapping H onto itself. That is, T1 comma T2 belongs to BD LHH. Then T1 plus T2 and alpha T1, where alpha is any complex scalar, are also members of BD LHH. Let T star from H to H be the adjoint operator of T from H to H, where T belongs to BD LHH. Note that T star belongs to BD LHH. Now, in this connection, we get a theorem, that is, T1 plus T2 star equal to T1 star plus T2 star, and for any scalar alpha, that is for any complex scalar alpha, alpha T1 star equal to alpha bar T1 star, where T1 star T2 star denote adjoint operators of capital T1 and T2 respectively. Now, we are going to discuss of its proof. For the first part, for all x comma y belongs to capital H, we have inner product T1 x comma y equal to x comma T1 star y, and inner product T2 x comma y equal to inner product x comma T2 star y. Now, inner product x comma T1 plus T2 star y equal to inner product T1 plus T2 x comma y, which is equal to inner product T1 x plus T2 x comma y, which is equal to inner product T1 x comma y plus inner product T2 x comma y, which is again equal to inner product x comma T1 star y plus inner product x comma T2 star y, which is equal to inner product x comma T1 star y plus T2 star y, which is equal to inner product x comma T1 star plus T2 star y. This shows that T1 plus T2 star equal to T1 star plus T2 star. For the second part, inner product x comma alpha T1 star y equal to inner product alpha T1 x comma y, which is equal to alpha inner product T1 x comma y, which is equal to alpha into inner product x comma T1 star y, which is again equals to inner product x comma alpha bar T1 star y. This being true for all x comma y belongs to capital H. So, we have alpha T1 star equal to alpha bar T1 star. Now, we shall prove the second theorem, that is T1 T2 star equal to T2 star T1 star. The proof looks like this. For all x comma y belongs to capital H, we have inner product
T1 x comma y equal to inner product x comma T1 star y, and inner product T2 x comma y equal to inner product x comma T2 star y. Now, inner product T1 T2 x comma y equal to inner product x comma T1 T2 star y, that is inner product x comma T1 T2 star y equal to inner product T1 T2 x comma y, which is equal to inner product T1 of T2 x comma y, which is equal to inner product T2 x comma T1 star y, which is equal to inner product x comma T2 star T1 star y, and this shows that it is equal to inner product x comma T2 star T1 star y. This is true for all x comma y belongs to capital H. Hence, T1 T2 star equal to T2 star T1 star. The third theorem is like this: for any t belongs to BDLHH, norm T star T equal to norm T square, which is equal to norm T star. The proof looks like this: we always have norm T star T less or equals to norm T star into norm T, which is equal to norm T into norm T, which is equal to norm T star, because T star belongs to BDLHH and norm T equal to norm T star. Thus, norm T star T less or equals to norm T square. This is equation number 10. Again, norm T square equal to supremum of elements norm Tx square, where supremum is taken over norm x less or equals to 1, which is equal to supremum over norm x less or equals to 1 of modulus inner product Tx comma Tx, which is equal to supremum over norm x less or equals to 1 of collection of all elements with modulus of inner product T star Tx comma x, which is equal to supremum over norm x less or equals to 1 collection of all elements with modulus of inner product T star Tx comma x, which is again equals to supremum over norm x less or equals to 1 collection of all elements with norm T star Tx into norm x by CS inequality, that is Cauchy-Schwarz inequality, which is again less or equals to norm T star T, that is norm T square less or equals to norm T star T. This is equation number 11. Thus, from equation number 10 and equation number 11, we have norm T star T equal to norm T square. This is equation number 12. Replacing capital T by T star and using T double star equal to T, we get norm T star equals to norm T double star into T star, which is equal to norm star of T star into T star, which is equal to norm T star square, which is again equal to norm T square by equation number 12, and this is named as equation number 13. Thus, from equation number 12 and equation number 13, we have norm T star T equal to norm T square, which is equal to norm T star. In this connection, we get a following corollary: if T is a bounded linear operator from H to H be such that T star equal to T star T, then norm T star equal to norm T square. Let us take a theorem. If Tn is a sequence of bounded linear operators from H to H and Tn converges to T as n tends to infinity, where T is a bounded linear operator from H to H, then Tn star tends to T star as n tends to infinity. The proof of the theorem looks like this. By the previous theorem, norm Tn star minus T star equal to norm Tn minus T star, which is equal to norm Tn minus T. This is equation number 14. Since Tn goes to T as n tends to infinity, Tn star tends to T star as n tends to infinity by equation number 14. Let us take another theorem. The adjoint operator on BDLHH is 1 and on 2. If T inverse from H to H exists, then inverse of T star from H to H also exists, and inverse of T star equal to star of T inverse. The proof looks like this. Let psi is a mapping from BD-LHH to BD-LHH defined by psi t equal to T star for every t belongs to BD-LHH. We shall now show that psi is 1 1. Let T1 T2 belongs to BD-LHH such that psi T1 equal to psi T2. So, T1 star equal to T2 star. We have star of T1 star equal to star of T2 star, that is T1 equal to T2. For T star belongs to BD-LHH, we have psi of T star equal to star of T star, which is equal to T double star, which is equal to T. Thus, for every T star belongs to BD-LHH, there is a T belongs to BD-LHH such that psi T star equal to T, which shows that psi is onto. Let T inverse from H to H exist. So, T inverse equal to T inverse T is equal to identity operator I. So, star of T inverse equal to star of T inverse T, which is equal to I star, which is again equal to I. Hence, star of T inverse into T star equal to T star into star of T inverse, which is equal to capital I, the identity operator. Hence, the operator T star from H to H is invertible. Thus, we have inverse of T star equal to star of T inverse. This completes the proof of the theorem. Note that for T belongs to BD-LHH, psi of alpha T equal to alpha T star, which is equal to alpha bar T star, which is equal to alpha bar psi T. This mapping psi is called the conjugate linear mapping. In this connection, we note a remark. From the previous properties of the adjoint operator T to T star on BD-LHH as discussed above, we see that the adjoint operator T from T star is 1 1 conjugate linear isometric mapping on BD-LHH.
In this module 1 of chapter 10, we have discussed on Hilbert adjoint operator T star for a given bounded linear operator T over a Hilbert space H onto itself. Also, we have discussed some algebraic properties of Hilbert adjoint operators. With this, we now come to an end of module 1 of chapter 10.